In this video, we're going to prove the theorem that is in front of you. In our previous video, we analyzed the statement of this theorem very carefully, and in particular, we looked at both of the hypotheses and figured out what they meant in terms of this particular theorem. So now it's time to actually turn our attention to the proof. And I'm going to do a proof by contradiction. So I'm going to assume, in other words, I'm going to let the pKs be a sequence that is known to converge to X. And this sequence has the property that pK is never equal to pK plus 1 for all k inside the natural numbers. And we are going to suppose, by way of contradiction, that X is not an accumulation point for the set of terms of my sequence. Now, I want to think about what that means. That means there exists an open interval that I'm going to call S that contains our point X such that S does not contain any element of the set of terms of my sequence with the element being distinctly different from X. And I want to think about what that particular statement means in terms of the number line. So here's a number line, and we're going to put X somewhere on this number line, and we are going to draw at the open interval S. So maybe this is S. Now, this statement here says that S does not contain any element of the sequence that is distinctly different from this X itself. So what I'm going to choose to do is I'm actually going to delete X and look at the set S take away the set containing X. And I want to actually highlight that set. That's going to be all of the numbers here up to but not including X, and all of the numbers that are bigger than X and up to the other endpoint of my interval. And now, what do I want to do about this? Well, what I want to say is the following. This statement up here says there are no pKs in those white line segments. So there are no pKs inside the set S take away X. And that's from our hypothesis that X is not an accumulation point for the sequence. But now I do want to remind you that we also know, as one of our main hypotheses, that the sequence itself does go to X. It converges to X. And this has some important implications on its own. So I want to look at that on the next panel. And since the sequence of pKs is known to converge to X, and S is an open interval, and X belongs to that S, there has to be a capital N inside the natural numbers such that if little n is bigger than or equal to capital N, then P sub n has to belong to S. This is the definition of convergence. The definition of convergence says no matter what open interval you pick, as long as X is in it, we have a way of trapping the tail inside the open interval. So I want to think about what this means in terms of my number line. So here's my number line again. Here's X, and I want to put S on this number line. So my S looked kind of like that. And what this stuff here says is this. If n is bigger than or equal to capital N, then Pn has to be inside S. In other words, the whole tail is inside this open interval. So the whole n tail is a subset of that open interval S. But I want to remember what we've also already established. What I want to remind you of is that if I delete that point X and I look at the set as takeaway X, which remember looks like this, there are no pKs in as takeaway X. And if you look at these two statements together, so these two statements together, they have an important implication. Put these together, and we find that if n is bigger than or equal to capital N, then Pn has to be inside S, and it can't be inside any of that white. Pn has to be equal to X. So Pn is equal to X. In other words, that point is P capital N, it's P capital N plus 1, it's P capital N plus 2, and so on. In other words, as long as n is bigger than capital N, Pn is equal to X. And now I want to think about what that means. But if Pn is equal to X for all n bigger than or equal to capital N, then we have a contradiction to our hypothesis that pk is never equal to pk plus 1 for all k inside of the natural numbers. I mean, right now, what we already know here is Pn is equal to Pn plus 1. That contradicts this fact here because n is indeed inside the natural numbers. In other words, what we have is this. If X is not an accumulation point for this sequence, and that sequence should be pKs, and the pKs do converge to X, then it turns out the tail of the sequence is going to be constant. And so what we then have is the following. So if the pKs do indeed go to X and the tail is not constant, then X is indeed going to be an accumulation point for the sequence. And that completes the proof.